Hi students, and welcome to chapter 11. So in this chapter, we are going to be learning all about chemical equations. We have spent the last few chapters understanding about one specific molecule. So we started at the very beginning of the semester learning about atoms, and then we put those atoms together into molecules and compounds. And now we're getting into kind of the third branch of chemistry here, where we start to put those molecules and compounds together in a solution or in a container together and see what kind of reactions come out of them. So in this chapter, we're going to be describing those reactions that happen when different molecules and compounds come into contact. So in this chapter, we're really going to be focusing on the idea of a chemical reaction. And a chemical reaction is a process, it's an event by which one or more substance gets changed into one or more different substances. So when we are talking about a chemical reaction, we need to see a substance change, a substance become something new. So this is not just like ice melting. That's a physical change, but we're instead talking about chemical changes. So this is things burning, this is different ions coming apart and coming back together to form new compounds. Just as a reminder, when we do these reactions, the substances that come before the arrow or that start out the process are called reactants, and the substances that come at the end are called products. And this is a chemical equation looking at a reaction. We can see a few different things here. The most important thing in this slide is that the reactants are the things that react, that go into the reaction, and the products are the items that are produced. We can see the reaction arrow that, like an equal sign, indicates that we have a reaction. We can see the individual subscripts, and these subscripts indicate how many of each atom are in each molecule. And then, last but not least, we have our coefficients, and the coefficients tell us how many of each molecule or compound we have. So the subscripts tells us how many atoms in a molecule, subscript telling us how many atoms are in a molecule or compound, and our coefficients are telling us how many molecules are in the reaction. So you can see right away that this chapter is taking what we already know about reactants and products, about molecules and reactions, and it is building upon that to make it into an even more complex look at our chemical reactions. So when we look at chemical reactions, there are really 5 kinds of chemical reactions. We can take most observable chemical reactions and we can file them as one of these kinds of reactions. The first one is called combination, and as it sounds like, we would put things together or combine them in this kind of a reaction. In decomposition, we're going to break them back apart. Single replacement, we're going to have basically a substitution. If you've ever played a sport, this would be like, we're going to send in a new pitcher, but everyone else stays on the field. Or we're going to send in a new setter, but everyone else stays on the court. Where double replacement, we have kind of a switch of partners. Like imagine that you're square dancing and you're going to switch partners. And then lastly, we have combustion, which produces huge amounts of heat and light and energy and creates explosions. So as we go through the chapter, we're going to be pausing to really gain an understanding into each one of these kinds of reactions. But before we begin that, we're going to spend some time looking at what we know about reactions in general. I just want to point out right at the very beginning that on page 366 in your book, there is a summary that kind of takes you through almost everything I'm going to be teaching you in the chapter in terms of types of reactions. If I were you having to take notes on this chapter, I would definitely have my book open to page 366 and 367 as I am going through and explaining the chapter, and I would be referencing those materials as you go so that you're not writing down things that you could otherwise just read in your book. So you're not taking extra notes that that you maybe don't need to write down, I would really use your book as a solid resource throughout this chapter. By the time we are to the end of this chapter, you will be able to look at an equation and identify which of these types it is. So for example, here we see Na plus MgCl2, or sodium plus magnesium chloride, becomes Mg plus NaCl, or magnesium plus sodium chloride. And you would be able to look at that and go, single replacement, obviously. And that's because we're getting the substitution. Sodium is substituting in for magnesium. But we will learn that. The other thing you will need to be able to do is, given the type of reaction, if I say this is a combination reaction, you would need to be able to predict the product. So the products of this would be MgCl2. And you would need to be able to look at these reactants and then fill in what goes on the other side of that reaction arrow. And lastly, and this is the last section we're going to cover, you would need to learn how to balance these two kinds of equations. So we will be learning a lot of layers all about chemical equations and chemical reactions in this chapter. We will be writing down lots of chemical equations and reactions. And so I really highly recommend that right from the very beginning, you have your notes out, maybe some multicolored pens, and you're really ready for taking some solid notes in this chapter. So we're just going to jump right into some equation basics. When two compounds combine, it is sometimes tough to decide whether or not a chemical reaction has occurred. So what we want to do is look for some of these signs, some of these symptoms, byproducts of a chemical reaction. We might look to see if the reaction is giving off light. Oftentimes when things burn, they are reacting chemically. We can also look for heat. Does the reaction get hot, or does the reaction feel cold to the touch? When you open one of the portable ice packs that you might find in a first aid kit, they kind of feel granular, they sound like there's salt in them, and you know that you're supposed to break this little packet and then mix them up, and the reaction that happens inside absorbs heat and feels cold to the touch. That change in temperature is a sign of a chemical reaction. Light, as we already mentioned, is a sign. Sometimes gas bubbles being produced are a sign of a chemical reaction. If you mix two things together and it starts bubbling and fizzing, like with the baking soda and vinegar that we did at the very beginning of the year, that kind of gas produced is an indicator that you are observing a chemical reaction. And last but not least, there is a process called precipitation. A precipitate is formed. And a precipitate is when you take two solutions, so two chemicals that are dissolved in water or aqueous, and you pour them together, and a solid rains out of the solution. A solid falls out and collects at the bottom. That solid is called a precipitate, and the whole reaction is called a precipitation reaction. You may have heard the word precipitation before. I happen to be making this video on a rainy day, and so rain is considered precipitate. It precipitates from the sky. It appears as if from nowhere from the sky, but we know that it's really up there. It just takes a particular weather conditions in order to precipitate that water falling from the sky, okay? It's like to force it to come, to allow it to form. That's what we mean by a precipitate. So when we see these types of symbols, these types of signs, we can assume that a chemical reaction has occurred. Now it mentions that heat and light are not proof positive that a reaction has occurred. This is because you can have things like a light bulb, and a light bulb is not necessarily a chemical reaction per se, but it is giving off light to the surrounding environment. So it's not proof positive, but it is a good sign or symbol that a reaction has occurred. When we write a reaction, we write it as an equation. So a chemical equation shows everything that is involved. So we can't have something understood. Flour and water, and that makes a cake. Well, there is flour and water in a cake, but that's not it. If I just take flour and water and throw it in the oven, I'm not going to end up with the cake. I've left some important pieces out. Well, you need sugar. Well, obviously you need sugar. A cake is sweet. No, there's no obviously. We have to list everything out. I actually think a really good analogy for a chemical equation is a recipe. If you think through a recipe, it's the same characteristics that we see in a chemical equation. So first of all, showing everything that's involved. Secondly, we need the correct formulas for the reactants and the products. And this moment right here is a revisit. Sorry, it's true, a revisit of chapter 9. In chapter 9, we learned how to take magnesium and chlorine and put it together to MgCl2 because we crisscrossed the charges and reduced. You will need that skill in this chapter. You will need to be able to crisscross and reduce and create those formulas in this chapter. We also need to uphold the law of conservation of mass, which says that the total mass before needs to be equal to the total mass after in the equation. But more importantly for us, the number of atoms before needs to be equal to the number of atoms after. And this part is where we come up with the idea of balancing. So in this chapter, we're going to be combining what we learned with chapter 9, and we're going to be adding to it and balancing those chemical equations in order to uphold the law of conservation of mass. So if we choose to look at this example once again of hydrogen, oxygen in the formation of water, what we can see about this chemical equation is that it's showing everything that's involved. If there's hydrogen on this side, there is hydrogen on this side, oxygen and oxygen, no surprises. Something that would not work in a situation like this would be to say H2 yields H2O. If I said H2 yields H2O, I would not be showing all that is involved. Another mistake I could make in this equation is I could not use the correct formula. H and O are part of the diatomic atoms that need to come as diatomic molecules. So I have the wrong formula. If I do something like that, I will never get this properly balanced. And last but not least, I need it to be balanced. So if I only had H2 plus O2 yields H2O, this would be unbalanced because what I'm essentially saying is I have two H's and two O's, and then I have two H's and just one O. Where did that O go? I can't just say like it disappeared. I have to be able to account for it. And so balancing allows for that accounting. So these are 1, 2, 3 examples of how we can see the characteristics of a chemical equation in a real equation. So what we're going to be doing now is just going through some of the other symbols that you might come across during the chapter to make sure that you feel comfortable with what they mean. So we will sometimes see written at the end of a formula a little letter in parentheses. This letter in parentheses tells us the state of matter that that compound is in. So if I see NaCl solid, I'm expecting salt, table salt, like in a salt shaker that I recognize and understand. If I see a symbol like an L in parentheses, that's telling me that it is a liquid. So if I see H2O then I'm expecting a glass of water. If I see H2O with an S, then I'm expecting a block of ice. If I see H2O with a G, then I'm expecting water vapor because G indicates the state of gas. So the state of matter is indicated in these little parentheses. I am not going to have you provide those symbols in parentheses, but I will sometimes provide them to you as hints or helpers throughout the equation. So they can be something that can be a guide or a helper as you go. The last state of matter that we need to talk about is this symbol of AQ, aqueous. An aqueous or aqueous solution is one where a solid has been dissolved in water. So if I take that solid NaCl and I pour it into my liquid water, I now have an aqueous solution of NaCl. So the AQ means dissolved in water. So it adds something else to the equation. We know that the NaCl is aqueous or dissolved in water. Our single and double replacement reactions are going to really like to take place in water. So you're going to be looking for this AQ when we get into our single and double replacement problems. Another helper you might get is a little arrow down. That would tell you that a precipitate is formed. Remember that a precipitate forming is one of the symbols or the signs that a chemical reaction has occurred. So if we see this symbol with the arrow down on the product side, that could be an indicator to us that we have seen, in fact, a chemical reaction. Alternatively, we sometimes get an arrow up, and the arrow up indicates that we are forming a gas or bubbles are forming in the solution. When we see the little triangle over the top, that means that we need to heat the solution in order to make it work. If you were imagining an equation for making a cake, we might say, okay, you need flour and water and eggs, etc. And then we draw the line and we would need to put a little delta over the top, because to turn batter into a cake, you must use heat. Heat is required. So that would be a way to show that you need to cook it or you need to heat it. We also sometimes see a chemical formula over the top of our reaction arrow, and that indicates a catalyst. A catalyst is something that speeds up the reaction without being consumed by the reaction. So it's not a reactant or a product. Instead, it's something that facilitates the reaction itself. And finally, last but not least, the double-headed arrow tells us that the reaction is reversible. That means it can go from the reactants on the left to the products on the right, or it can go vice versa, from the products back to the reactants, that both directions are happening in a live situation. So these are all symbols that you may see, and once again, could prove to add just a tiny bit of information to what you're studying and maybe help make the equations make more sense.